or understand wavelets. And I'm going to look at a particular one. First, a little bit of the history. My connection with wavelets started in the late 1980s. I read a paper by Ingrid Dobische, and it was an amazing paper because it introduced me to a new type of mathematics that I had never thought about before. Wavelets actually started many years before that, but in 1988, Dobische published a paper that caught the attention of the digital signal processing world. So many people in seismic signal processing, speech processing, image processing, medical signal processing, many areas use wavelets. Some with success, and some it was no better than traditional techniques. But it was extremely exciting, and over the past 10 or so years, wavelets has developed into a fairly mature subject. Here I have listed some of the people who have contributed to wavelets. The point of view that I will take is more like Dobische. She is currently a professor of mathematics at Princeton and was the first woman professor of mathematics at Princeton ever. So she's quite famous, and there's not that many women who work in mathematics, so she's rather special. In the signal processing world, work came out of Georgia Tech by Tom Barnwell from the point of view of filter banks. So they looked at the wavelet as a particular type of multi-rate signal processor. Dobische looked at it as a signal expansion problem. Work at Stanford by David Donahoe on compression, denoising, and other types of wavelets were rather important in the late 90s. A book by Barbara Hubbard, The World According to Wavelets, is a popular book. It's a history book, but it talks about wavelets from the point of view of a microscope or a telescope, or multi-resolution. Lynn Swellens, the last reference here, out of Bell Laboratories, did some extremely interesting work, somewhat like I'm going to talk about in a moment. Well, the first question I think that anyone would ask is, what is a wavelet? Unlike a sine wave, a wavelet is much more general. So the question is, what is it that we do when we talk about wavelets? Well, the first, it is a linear composition. So we take a signal and express it as the sum of basis functions, of weighted basis functions. So at the very beginning, the wavelet is a linear decomposition. So if you're looking for a way to do nonlinear analysis, this may not be the way to do it. It's basically linear. You break a signal down into parts, you work on the parts, then you decompose it. Another characteristic is that the wavelet is local. It's local in time, it's local in space, it's local in frequency, it's local in wavelength. So one of the characteristics of the wavelet is that it localizes something, the information, the energy, something in the signal. And the last very important part is it's efficient to calculate. If the wavelet was very expensive to calculate, it would not be interesting. Okay, now what else is important? Most, not all, but most wavelets come from taking a single function and translating it, moving it back and forth, and expanding it or compressing it. So you see in the first equation here that I have a function, psi of t, and I translate it with the integer k. So So K1, K2, K3, K4, K5. I expand it or compress it with the exponent J. So the multiplier on T causes the function to get wide or narrow. So with those two parameters, K and J, I have a family of functions. Okay, do we have something similar to the Fourier transform? And the answer is yes. Frequency is the expansion factor. And the difference between the sine and the cosine is the shift factor. It turns out for the sine wave, there are only two components, sine and cosine. And if you move further, it brings back to sine and cosine, sine, cosine. So that's not so interesting. But the translation is sine and cosine. And the dilation compression is the frequency. So the sine wave is a little bit like a wave. The second point here is the most important probably of all, and that is the so-called multi-resolution requirement. And that is that the function phi of t can be represented in terms of phi of 2t. So I have a function that can be represented in terms of the same function half the width. Now that may seem like a strange requirement, but I will explain more to you more of that in just a moment. Here's an example of a wave and an example of a wave. You see here why the wavelet concentrates or localizes information, where the wave does not. The wave localizes it in frequency, but not in time. The wavelet can localize it in both. Here is the statement about translation and about scaling. This idea of starting off with a single function. Since Ingrid Daubechies is a woman, she called it the mother function. Maybe if it's been invented by a man, they call it the father function. And here is the example of some Daubechies wavelets. At the bottom, you have the basic wavelet, translated K1, K2, K3, K4. Then you make J larger, which shrinks the size of the wavelet, and they're K1, 2, and so forth. So you have both parameters. You have J on the vertical axis, K on the horizontal axis. This is a family of functions. This, the multi-resolution formulation, is something that's extremely important for you to think about. It doesn't show up explicitly in the filter bank approach. But when you take this approach, this is the most fundamental idea of all of wave theory. And that is that if I look at an image and then I walk closer to the object, I see more detail. And if I walk closer still, more detail. I step back, less detail. Step back, but it's the same image. So the high resolution version of it contains the lower resolution version. So that's the idea of multi-resolution, that you require that these spaces be contained in one another. The low resolution is contained in the high resolution, is contained in the higher resolution, is finally contained in the entire space of function. So as you shrink the space, you lose resolution, but you still have the option. So it's like looking at a person from a distance. You can't tell what color their eyes are, you can't tell the details, but you can tell it's a person. If you get far enough away, you can't even tell it's a person. So you come in close, more detail. You step back, less detail. And here is the mathematics of it. L2 is the space of all square integral functions. Signal with finite energy. And on the left, you have the empty space, and everything in between gets larger and larger in detail, or smaller if you're working on the graph. Look at the equation in the box. Does that make sense to you? What I'm telling you is the equation is the same information that's in the multi-resolution setting. Is that I can always write this space in terms of the larger space. I can write it in terms of the still larger space. So phi of t can be written in terms of phi of 2t. That's my requirement. Now here's the question I ask you. In this equation with the box around it, do you know what, does that define phi of t? If I were to tell you that 3 times the second derivative of a function plus 2 times the first derivative of a function plus 7 times the function is equal to 0, that defines the function. It's a differential equation. And you know how to solve differential equations. I give you the equation, you can find the solution. This is a different kind of equation. It's a multi-resolution equation. But it also has a solution, a unique solution. So when I write this down, if I give you the h of n, you should be able to tell me what the phi of t is from this equation. Now, I don't think you actually can because we're actually not studying this, but it's possible. So this equation is equivalent to a differential equation. In traditional dynamics, you have a differential equation, it has a solution. In multi-resolution analysis, you have this resolution equation. It also has a solution. Now here is the wonderful thing, I think, about waves. In Fourier analysis, you start with a sine function and a cosine function, and you build a transform system. And then you look at the properties of that transform system. For wavelets, you decide what you want the solution to look like, and then you work backwards. I don't know what phi of t is. I do know what a sine function is. I start with a sine function, and then I create the transform. But here, I want the properties to be multi-resolution and to localize. What kind of basis function should I use? The solution to this equation is the answer. So to me, this is the proper way to formulate a problem. You formulate the problem, you discover what the basis functions are. You don't assume the basis function and then create the transform. So it's really backwards. No, in fact, it's forwards. What's backwards is what Fourier does. Start with the sinusoids and develop a transform. Or perhaps start with polynomials and develop a transform. Wavelet analysis starts with the properties and discovers what the basis functions are. And those basis functions can be different for different problems. Dirichlet wavelets have certain properties. There's other type of wavelets that fit other type of problems. Whatever your problem is, you need to find the proper wavelets to solve that problem. This flexibility did not exist with previous transforms. And to me, one of the very interesting aspects of wavelet analysis is it allows you to optimally choose your basis functions and then discover what they look like. And actually, they look like strange. Now here is an example of a square wave, which is a wavelet, by the way. And you can see that the large rectangle can be written as the sum of two small rectangles. Or a triangle wave is a wave. The large triangle can be written as the sum of three smaller triangles. So you see how the large functions can be written in terms of the small ones. So the triangle wave is the solution to the equation underneath it. The rectangle is the solution to the equation underneath it. So I am developing a theory, and it has nothing to do with filter banks. You can develop the same ideas from the point of view of filter banks. But it's possible to do it this way and not ever talk about filter banks until you reach the end. Because also possible to do just the opposite. Okay, now what do waves look like? Well, here's an example. It's a particular example, and I think, there are 6 parameters, I think 6 scaling functions. The one in the upper left-hand corner is very good for image processing because it's symmetric. It's like an FIR filter. By being symmetric, it means the picture does not look smeared out when you express it in terms of this wave. The wavelet in the upper right-hand corner is maximally differential. It's the smoothest of all of those waves. Is that good? I don't know. Depends if you want smooth waves. That's what you use. The one in the lower left-hand corner is often used for solving partial differential waves. What does that mean? It means that you form the solution as a sum of wavelets. You can turn a partial differential equation into a system of ordinary differential equations. And if you do it with wavelets, it's a fairly small system, and so you can solve it efficiently. So wavelets are often used for numerical solutions of partial differential equations. So are Fourier transforms. But with Fourier, you don't have this ability to choose the optimal waveform. In the lower right-hand corner is a fraction. So these things are not only possible for them not to be differential, they can even be fractal in nature. Perhaps that will suit your signal better than a smooth one. So here are 4 examples. Look very different from each other. But there are 4 examples of basis functions you can use to analyze signals. Well, those functions that I showed are actually not wavelets. They're what are called scaling functions. So you need to define wavelets.
Get another one.
I think our battery is fine. Oh. The wavelets found different basis functions. The wavelets are the difference between the scaling functions. So when we define our wavelets, they are defined in terms of the scaling function. Now this is a detail that's not particularly important, but if you define in terms of scaling functions, you have these nested spaces. The wavelets are defined as the difference between the spaces, so they do not overlap each other. You add 2 wavelet spaces to get a larger wavelet space, and so forth. But that's a detail that's not that important. And the upper equation tells you that any square integral signal, if you have a signal, if it has finite energy, then it can be written as a sum of scaling functions and wavelets. So the first summation there is a scaling function. The second one, which has 2 sums, is the wavelet. How do you find the coefficients, the C and the D? You find it with an inner product, the same way you find Fourier coefficients. How do you find the Fourier coefficient? You take your signal, multiply by cosine, you take the integral. You get a number. The next Fourier series, you take it and multiply by the cosine of 2t, and you get another number, 4t, so on and so forth. Here, you multiply the signal times the basis function, take the integral, you get the coefficient. The same as you do with Fourier series. So it's the same concept of a deconstruction and a reconstruction as Fourier, but it's based on a different set of functions. Something that's extraordinarily important. Perhaps you know this, and perhaps you don't. Parseval's theorem. Do you know Parseval's theorem?
Yeah.
Yes. Your professor said yes. So you must know Parseval's theorem. Parseval's theorem is very important. If Parseval's theorem were not true, you could not talk about energy in the frequency domain. If I tell you that this signal has energy in the low frequencies and not so much in the high frequencies, I am assuming that Parseval's theorem is true. Because to talk about the energy of a signal in frequency domain and have that imply something in the time domain requires Parseval's theorem to be true. Okay, it turns out that Parseval's theorem also works for wavelets. I can decompose wavelets. The energy in the original decompose of a signal in terms of wavelets. The original signal, its energy, is the sum of the energies in the different components. That's not true for all transforms. It is true for orthogonal basis functions. It also turned out to be true for another set, and that's in terms of what are called tight frames. Another detail is not too important, but it turns out that Parseval's theorem works not only for orthogonal basis functions, but for a larger class. That wasn't particularly important until wavelets came along. And now it is. And you need to know something about frames and tight frames and things like that. So somewhere in your studies, try to learn something about frames and frame decomposition. Right now, I would like to show you the relationship between this discussion I have given you and a filter bank discussion. So I write these two equations here. I start with the multi-resolution equation, the one that I told you was the foundation of the universe. It's everything. And from it, I write down these two equations here. If I take these two equations and express them in terms of a block diagram, this is what it looks like. What I have is a signal coming in on the left. It passes through a filter, H1, and then I take every other sample. I sample it down. So if it's coming in and I have 10 samples, I take 5. I pass it through a different filter, H0, and I take half of those samples. Now the lower one, I do the same thing it did. So I keep down sampling. In the lower right-hand part of this picture, the data rate is very slow. Okay. In the original signal, it's very fast. The number of sample points is the same. We have neither lost information nor added redundant information. It's as I split it into two and take every other sample. 10 samples gives me 5 and 5. Still 10. I should choose 5. 16, 8 and 8. And then I take the lower 8 and I take 4 and 4. And then I take the last 4 and take it to 2 and 2. But the total number of points coming out is exactly as the same as the total number of points coming in. So the information is still there. All of it. None of it is lost. And none of it is redundant. So I don't have too much nor too little. Sometimes I want redundancy. Sometimes I'm willing to accept loss of information, a little bit, not much. And that's possible. But right here, there is no loss and there is no redundancy. This is a filter bank. Traditional theory doesn't understand this. You have to understand time-varying filters, downsampled filters. And that's kind of a study by itself. That's so-called filter bank theory. A number of groups in the world have developed the entire theory from filter banks. And a good friend of mine, Tom Barnwell at Georgia Tech, he always used the filter bank approach. I prefer the signal expansion approach, but they're the same. It's just two different ways of looking at it. In the case of filter banks, you will sample. that causes aliasing. So the upper signal will have information that is added to the lower signal, gives you the total together. So you run into a low-pass filter and downsample. There's some aliasing. You carry along with it some information unaliased the upper. And you keep doing that over and over. But the difference pieces require very few bits for representation. So you end up with the ability to save information looking at it from this filter bank point of view. The same thing you can look at it from the signal expansion point of view. I take the output of the previous filter bank, I feed it into this filter bank where I run into a filter, I first upsample, put zeros between each number, run into a filter that interpolates, put zeros between, run into another filter, and when I finally finish, I have exactly what I put in originally. Well, that's a bit strange. Why would you want to do something and then undo it? And the answer is, in the middle, you can kill it. In the middle, I will throw away many of the components. Now, here is one of the interesting characteristics of this system. When I take the wave transform, I discover that the majority of the coefficients are very, very small. So I just throw them away. And I end up with a very small number of coefficients. When I reconstruct it, I get a signal that's very close to the original. Because what I threw away is small energy. Parseval's theorem says it has small energy. So this is a method to compress signals. If you just take the signal itself and try throwing away some of the components, it will be a mess. Or if you take Fourier analysis, it's not as good. But here you're able to compress signals in a very efficient way. And something I will show you in a few moments that I find just astonishing is that you can take these signals, and when you throw away the small ones, most of the small ones are noise. And when you reconstruct it, you can remove the noise from the signal. So it's a very interesting filter, or so-called denoising system. And it's possible to denoise a signal without removing sharp edges. You cannot do that with Fourier analysis. With Fourier analysis, when you remove the noise, you also remove the sharp edges of the signal. So you smear out things in the time domain. And if you're doing, say, seismic signal analysis, or medical signal analysis, or certain types of image signal analysis, the sharp edges are very important. You do not want to lose them. So perhaps the waves are good for that, because you can remove the noise and retain the sharp edges. So it's not as simple as I say. It can sound, but anyway, that's part of the idea. Let me now tell you what you can do to make this a more general system. The original wave expressed a signal in terms P of t in terms of P of 2t. In this first point here, I'm going to express P of t in terms of 3t, or 4t, or mt. So I can express it in terms of numbers other than just 2. So rather than stretching and compressing the signal by 2, I can do it by 3, or 4, or 6, or 8, whatever you wish. So one generalization is to use a number other than 2. Why would you want to do that? Why would you want to use an expansion other than 2? Well, it turns out that some signals, when you decompose them like this, do a better job of concentrating the energy and concentrating the signal information and eliminating the noise or eliminating redundancy than using 2. So we use a factor of n. By the way, if some of you end up doing research, and I hope many of you will, one of the things you'll discover is in developing a research program, you take the knowledge that currently exists and try to make it more general. So if you know how to do linear time invariant circuits, well, the next thing you do is look at linear time varying circuits and see what you can do. Then, after you solve that problem, which I will be delighted if you do, after you solve that problem, you should solve nonlinear circuits. And of course, that's an incredibly difficult problem, and you will spend all your life working on that. But the idea of always taking a problem and going and relaxing the constraints, what were the assumptions that were made? Well, see if you can drop some of the assumptions. So if the assumption for the wavelet was that you express a function in terms of this same function of 2t, try 3t, try 7t, try something else, see what happens. So it's a discovery process. The other thing you can do is, in addition to taking the filter bank that I showed you earlier and splitting the lower branch over and over again, split all of the branches. So you can develop a very rich system by iterating these equations on the various branches. Another thing is expand the signal with a few terms, then switch basis functions and expand the remainder in terms of another set of basis functions, and then switch basis functions again and expand it in terms of still another. You don't have to use the same set of basis functions for the entire expansion. So it's possible to use several sets of basis functions. In fact, you can even mix wavelets in Fourier. Take a signal, expand it for a few terms with Fourier, then take the remaining part and expand it with wavelets, or vice versa. So the idea of switching basis functions during an expansion is something that's new. It's not new now, it was a few years back, and it opened up some very interesting possibilities for wavelet analysis. The early theory was in terms of orthogonal wavelets. And of course, after that was developed, the first thing you did was drop the requirement that it be orthogonal. Some systems are taking pictures of fingerprints and compressing them. You can do a better job with non-orthogonal systems than with orthogonal ones. And there are many signals where non-orthogonal expansions are better than orthogonal. And it turns out they're not that much more complicated. And as I mentioned, the idea of using frames rather than basis functions has some advantage. Usually, removing redundancy, I just want to change slides quickly. The having redundancy in some cases is an advantage. And usually, it's not. Usually you do everything you can to remove redundancy. But there are situations where redundancy helps you. If you have a redundant expansion of a signal, it is less affected by noise, often, not always. But often noise is less of a problem with a redundant system. And so if you have a problem with round-off noise or signal noise, sometimes a redundant system using frames rather than basis functions has some advantage. Of course, if you lose the compression, the whole idea of compression is to remove redundancy and sort of working in the opposite direction. But in the case of denoising, sometimes redundancy is desirable. All right, let me move on. What's our time looking like?
15 minutes?
Okay.
Oh, can I have questions?
Let me go to, let's take a look at this particular example. In the upper left-hand picture, we have a chirp signal. This is a signal whose frequency is changing and whose amplitude is changing simultaneously. So in the upper left-hand corner, you have that. In the upper right-hand corner, we have added noise to it. Now, if you try to filter that with Fourier analysis, it's a mess. It gives very poor results. So using traditional wavelet analysis, you get the lower left-hand corner. Using a redundant wavelet decomposition, in the lower right-hand corner, you've done an amazing job of removing the noise without distorting the signal. So both the frequency change and the amplitude change is recovered, and virtually all of the noise is gone. And that's a place where the redundancy helps you in the denoising. It hurts you in terms of compression, but it helps you in terms of denoising. Let me stop just for a moment and make sure you understand this idea of denoising. If I have a signal, and if I can compress that signal into a few coefficients, from Parseval's theorem, it tells you that those coefficients can be large. I have my signal, it has a certain amount of energy. I put it into the wavelet system. Most of these coefficients or some of the coefficients are very large. I take the others and throw them away. Just cut them off. I run into a threshold and remove them, set them to zero. If the noise is with the signal, the noise will have its energy uniformly distributed over all the coefficients. I would assume the type of noise it does so. So all of the noise is quite small, again, from Parseval's theorem. So the small noise and the large signal in the wavelet domain. The time domain wasn't that way. But in the wavelet domain, we made the signal get bigger and the noise get smaller. Then we just cut the small stuff off. We threshold and make all the small stuff zero. Then when we reconstruct the signal looks amazingly good and the noise is gone. I don't mean the noise is small, I mean it's gone. You can't see it. It's amazingly good, and this is what is happening in this particular example here. Another example of the same phenomenon. This is the skyline of Houston, the city where I'm from. And so I took this upper left-hand picture and used that as a signal, added noise to it, and used the two different methods of denoising. And the lower right-hand corner, okay, some of the noise did creep through, but most of it is gone. What are some of the applications? Well, right now, one-dimensional wavelet theory is fairly mature. It's fairly finished. It's understood. There's not a lot of need. Multi-dimensional wavelet analysis is still a pretty active research area. So image processing, multi-dimensional signal processing is still developing in the wavelet world. But you find a whole variety of applications that have found use in wavelets. I had a person sitting in on my course, my wavelet course, a few years ago, and he was using a wavelet system to model economic pricing. And I just was astonished. I was expecting some communication or some seismic or something, but he was modeling the price of oil or something. I don't know what.
Did he make $1 million?
Pardon?
Did he make $1 million?
He wouldn't tell me what his details are. I thought it was interesting. If it had been a technical person, yes, but an economic person, no.
What is noise in his picture?
Pardon?
What is noise in his picture?
What is the noise in his signal? In his economic, his student.
I think he was using it not for noise or compression, but using it more to look for trends and to see if he could find components that can carry more information, and so he could predict the future prices. And of course, if he can predict the future prices, that you can use that to advantage. The only problem is you can predict the future prices, and then you do something with that, it destroys the prediction. But many people do it. Okay, I think that's what I wanted to say about the application. What do I think is happening with wavelets? One is, I think they are a standard tool. And that in the past, query analysis is taught to undergraduates, and wavelet might be taught to graduate students. More and more, you're discovering wavelets being taught to students who are still undergraduates. Special wavelet systems are being developed that fit a particular application better than the original wavelets did. The use of wavelets for speech analysis, we thought that was going to be terrific. And it turned out it hasn't worked out as well as people had hoped. It seems that signals which are multidimensional have more redundancy and they are better suited to wavelet analysis than low-dimensional signals that have less redundancy. So perhaps more with images than with just one-dimensional signals. A variety of other applications will be coming along, I'm sure. Here are some of the references, and there are many research papers. These are just some books, and the book, of course, that I'm most fond of all is the last one, because I wrote it. And, so it's developed exactly the way I would do it. Thank you.
Dr. Burrus. I want to say that wavelets is rather difficult to understand. I myself don't understand about wavelets very much yet. But I can see that it is rather interesting and is widely and have wide application. And I really want to learn about what it is. But I can see that it's very difficult. So could you help me how to start, how to get things started, starting with what it is?
That is hard to answer. But let me tell you that there's another way to think about this. And that is, to understand wavelets, you don't have to do calculus. There are no derivatives, there are no integrals. Everything is done in terms of sums and finite sums. So it's possible to work with wavelets and not even understand calculus. I'm stretching it a little bit. But in some ways, because wavelets are discrete, it's possible to think about it. For people who have studied calculus, then of course that's a different story. But I think that some of the ideas from wavelets are actually easier than traditional Fourier analysis. But they're different, they're quite different. It requires a different way of thinking. But if you first start thinking when you're a second-year student or first-year student, thinking in terms of this, I don't think it's so difficult. And if you work, you try examples, you work assignments, you use computer models, I really think you can learn it as quickly as you can learn Fourier analysis. And Fourier analysis is not easy either. In the early days of electrical engineering, people thought that engineers could never understand calculus. It was too difficult. Okay, now we teach calculus to freshmen and sophomores, so it's not too difficult.
Hi, Mr. Burrus.
First of all, I have to say that I'm very lucky to sit here and listening to one of the representatives research in the ESP, and I have a question to you. As you said that with it, as I understand, is localization both in frequency and time. And this morning we have studied that the short time window transform
So how Fourier transform?
Fourier transform. I think it's localization in both frequency and time too. Can you distinguish two transform?
Yes. It's not easy to explain what you mean by localization, because if I have a signal and I take its transform, the entire signal is in the transform, so there's nothing lost. It's not like there's information lost. So I know those time intervals. But which parameters are easy to see? And with Fourier, when you take a Fourier transform, you can see the different frequencies. But when things happen, it's not so easy. You know, if you have a seismic signal, so that a signal happens at a point in time, if you look at the Fourier transform, it's very hard to find out where that energy is. There's a relationship that's called the Heisenberg uncertainty principle. And it tells you that if you take a system and localize it in time, the frequency gets wide. And if you localize it in frequency, time gets wide. And if you've ever seen the transform of a square wave, it looks like a sine x over x. And if you make the square wave narrow, the frequency gets wide. You make the square wave wide, the frequency gets narrow. So it's a trade-off. The wavelets do a better trade-off than Fourier. And in fact, in some ways, they're the best that can be done. So there's always a trade-off. And so if you want to have something localized in time or frequency, with the wavelet you can control that trade-off. With Fourier, it's not so easy. It can be done, but it's not so easy.
I have a question. I think this is the first time just about whether it's so it's difficult to know. But I know it's cutting edge program. So can you give some application, framework application in the world, so we can have communicate about whether this application?
Well, both the denoising and the compression characteristics are used. For example, there are some music compression schemes that use wavelet decomposition. So you take music, you decompose it in terms of wavelets, you take a small number of coefficients, record it, same as the MP3, which is a different set of coefficients, and at the other end, when you play it back, it sounds better. But it's not enough better. The trouble with music is that it's not enough better that it's, MP3 is still random. Wavelets is not quite compatible. Nevertheless, wavelets will do a better job. It's just only slightly better. The same thing for image compression. For image compression, the wavelets will do a very good job of, if you make a DVD or something, can you compress the signal so it doesn't use so much space? Yes, you can, but it's something that is expensive. Denoising. If you're going to denoise medical signals, you take X-rays or something, and you would like to remove noise to see the X-ray picture. Wavelet decompositions can be used there. And there's a variety of electronic communication systems where wavelets are the foundation of them. And the wavelets expand the signals in the logarithmic scale. Perfect. So it's going to be wonderful for speech. It's okay. It's good, but it's not wonderful. And part of the reason is that the ear and the wavelet are not that similar. And it's too bad, because if they were, it would be a nice result. But the compression depends on the use. And MP3 works because people hear music and it sounds pretty good. And if the way the music sounds better, well, it's not enough better. So they don't switch and stay with MP3s.
As far as I know about the DSP, equation we use is linear equation. And in your lecture, you also use linear decomposition in wavelength theorem. And but in the end of your lecture, you said that in the future we will use nonlinear decomposition to for the wavelength theorem. So I want to ask how nonlinear decomposition can be used, and what kind of nonlinear decomposition can be used?
If I could answer that, I would get still another PhD. That's a research question. And in nonlinear analysis of any sort, the nonlinearity always has to fit the particular application. Almost never can you have general nonlinear analysis. You can have general linear analysis, but once you start developing nonlinear system, it almost always has to be attached to a particular application. And I did some work many years ago in nonlinear analysis, and it's just awful. I mean, it's just an incredibly difficult problem. Convolution doesn't work. Nothing. All of your superposition doesn't work. Partial theorem doesn't work. Nothing works. Laplace transform, Fourier transform, all of the tools that we have do not work for nonlinear analysis. So it's a very, very difficult problem. Most of the systems that we build are linear. That's not because linear is best. It's because that's not what we know how to do. If we knew how to do nonlinear, what you're asking is, if I knew how to do that, if I could tell you that, it would be great, but unfortunately I can't. But I would encourage you, you're much younger than me, work on that problem, maybe you will solve it.
I have heard that the wavelength is a very hot topic now. I have a lecture in seminar in the university in wavelength. We have a main topic in this summer seminars in wavelength, and I have listened to the very interesting talk of you about wavelength. But all of those is the general wavelength. I want to, if you can show me some research orient, some narrow research orient of wavelength that you think that is very promising in the future.
Wavelengths are new enough that many of the applications are not discussed. If a company discovers how to use wavelengths to do something, they don't tell other people. That's the way they make money. Is they use that for some competitive advantage. It's only after something becomes kind of standard that everyone talks about it and you teach it to students. Many times in my own life I've seen problems where I knew in industry people had this information, but they wouldn't talk about it. So many of the real applications are not being openly discussed, but you know that they're happening because I know the people that are doing the work, and I know that they know waves, and I see the results come out. But it's just another signal processing tool. You should look at it as just simply another tool. Many tools that you have. It's not an answer. It's a method of obtaining an answer. So if you're trying to do a communication problem, waves is one method to look at. But there's many other things as well. I've only talked about them as if they're the only answer. That's not true.
Quite a bit about web transform, and in recent years, I know a group of people trying to develop a second generation. Can I hear from you some of the prediction or some idea whether the second generation will be replaced in the first one? Because I know web transform is already good for many applications.
I will be speaking next knows more about that than I do. If you want to know about the first generation, I know that. The more recent work, I cannot say. I just simply, if I make a prediction, it will be a guess. And you might ask Professor Vernon what he thinks about that. And, he can guess more accurately than I can.
Any other question?
My involvement with DSP I was very lucky because I started doing DSP when DSP came into being. my PhD was the same year that Cooney and Tukey discovered the FFT algorithm. And so when I saw that, I knew that this is a wonderful result, and I wanted to grab it and do something, and I did. But 10 or 20 years later, it was very difficult to do anything new with the FFT. It had already been done. But then we moved in to work in filter design, and we now have design filters. And so then I do some work then with waivers. Well, okay, waivers is now becoming mature. So part of what you see happen is ideas come along. If you can catch an idea when it's going somewhere, you can ride that up, and you're lucky. And then once you get near the top, you need to look for another idea. Don't keep riding that idea. It's gone. So part of what I was telling you about the way to do research is take something like waivers, look at the restrictions, see if you can think of an idea to remove those restrictions. Then multi-resolution. What if you don't insist on multi-resolution? Just simply say that it has, most of the energy has to be contained. Maybe you can have a still more general description. Or perhaps you can come up with a special